Hello everyone. Today we'll be continuing our discussion on random variables. Let me recall what we have studied so far. So we have proved that maximum of two random variables is a random variable. Similarly, minimum of two random variables is a random variable. We then extended that result to maximum and minimum of finitely many random variables and then infimum and supremum of countably infinitely many random variables, right? On the similar lines, we can extend the result further and we can prove that limsup and liminf are also random variables. Can you at least quickly think of the idea of this proof? Correct. So what we do is limsup is again infimum of supremum of something. Similarly, liminf is supremum of infimum of something. And because we have already proved that infimums and supremums are random variables, it is easy to extend the result to limsup and liminf. Okay. Similarly, limit, because limit is nothing but limsup or liminf when they are equal. Hence, it can be proved that limit of a sequence of random variables is also a random variable with respect to the same sigma field. Okay. We are not writing down the detailed proof, but I hope you are getting the idea that I am suggesting. Okay. Then we went and defined partition. A next step to that would be defining what is known as measurable partition. Okay. What is a measurable partition? Any partition A, if I define it as say A1, A2, AK, we will call this as a measurable partition with respect to omega script A if and only if AI is in script A for every I. Okay. So basically, if every set from that partition is in the sigma field, then we will say it's a measurable partition. Okay. And then we define simple random variable. So when you say something is a random variable, you need that partition to be measurable. Why do we need it to be measurable? Let us go to the definition of simple random variable and it would be easy to understand. How did we define simple random variable? We defined simple random variable x going from omega script A to r script B as x of omega is equal to sum over ai, indicator ai of omega, I going from 1 to k, right? Now, why do we need the partition to be measurable? See, if I take inverse image of singleton ai under x, so x inverse of singleton ai is going to be capital AI, correct? Why? Because that is how the random variable is defined. So if this is a1, if this is capital omega and if this is a1, we know that everything in here goes to single point a1 on R. So inverse image of singleton a1 would be entire capital A1. And we want x to be a random variable, right? So for x to be a random variable, this must be in script A. Hence, while defining a simple random variable, having just partition is not enough. We need actually a measurable partition. A measurable partition means a partition whose every set is in script A. Okay. Same thing goes with the elementary random variable. Even for elementary random variable, I have to start with a measurable countable partition. Okay. Now that we have appended the definitions of simple and elementary random variables, let us go one step ahead. We will now try to prove that functions of simple random variables can also be simple random variables. So this is known as algebra of simple random variables. Okay. So what do I mean by this? So if x1 and x2 are simple random variables with respect defined on omega script A, so both are random variables with respect to the same field, then x1 plus x2, x1 minus x2, x1 into x2 and x1 by x2 if it is defined, because we need to have x2 to be we need all values of x2 to be non-zero, then only it would be defined. So these are also simple random variables on omega script A. Okay, this is an important result. Now, there are a couple of things that I would like to clarify. First of all, when I say x1 is a simple random variable, it means that yes, there is some partition of omega, some measurable partition of omega on which we can define x1 as summation ai indicator capital AI. Now we are saying x2 is also a simple random variable on same omega script A. But remember, we are not saying that the partition for x2 is same as partition for x1. Okay, we just want partition for x2 to be another measurable partition. So it is possible that x1 is a simple random variable with respect to which is defined with respect to one partition. So x1 is summation ai indicator of ai, I going from 1 to k, and x2 is summation bj indicator of bj omega, j going from 1 to say m, where a1, a2, ak and b1, b2, bm are measurable partitions of omega. Okay, so both need not be defined on the same partitions. Now the question arises, how do I define x1 plus x2 or x1 minus x2? So let me try to draw a picture. Suppose this is my omega. Okay. Okay, suppose this is a1, a2, a3, a4, a5, a6. Okay, this is my first partition, but we just said that for x2 we may need other partition. So suppose this orange lines denote another partition. So suppose I have something like this. Okay, so this orange thing becomes b1, then this suppose becomes b2, this orange portion. Okay, this next big thing becomes say b3, this is say b4, this is b5, this is b6, but as I said we don't have to have same, so let me call it b6 and this is b7. Okay, we need not have same number of sets. Now when I want to define x1 plus x2, I have to worry about both the sets. So we know over a1 value of x1 is small a1 and over b1 value of x2 is small b1, something like that. Okay, so what happens in this portion? So say for example this part. In this part x1 is a1 and x2 is b1. Okay, so in this part my value of x1 plus x2 becomes a1 plus b1. Okay, whereas if I go to this part, only this much, then I am still in A1 as far as first partition is concerned, but I am in B4 as far as second partition is concerned. So it becomes A1 plus B4 over here. Okay. Then in this portion, in this part, it becomes A4 plus B4 because it is common to A4 and B4. Okay. Similarly, say if I focus on this part, this is coming from B2 and A5. So here it is A5 plus B2. Are you getting what I am trying to show here? So, given any omega, we have to check which AI is it in and which BJ is it in. Depending on that, value of x1 plus x2 would change. Same thing would happen with x1 into x2 or x1 x1 minus x2 or x1 upon x2. Okay. So what we are doing is, we are saying that we kind of have multiple possible values now. So even though for x1 I had a1, a2, ak, k distinct values. For x2 we had b1, b2, bm, m distinct values. But now for x1 plus x2 we are going to have combinations. a1 plus b1, then a1 plus b2, so on a1 plus bm, then a2 plus b1, a2 plus b2 and so on a2 plus bm. This goes on till ak plus b1, ak plus b2, ak plus bm. Okay, so we have k into m possible values, and how are they defined? So it depends on which ai and which bj the omega is in. So basically we have to talk about intersection. So this first green region, is actually intersection of a1 and b1. Hence it became a1 plus b1. Okay. So what we will do is, we will define a new partition. So Cij as ai intersection bj, and it is defined for every I and for every j. Okay. Cij is ai intersection bj and it is defined for every I and every j. So how many Cij's would I have? I would have k into m sets. Now first question is Cij, I going from 1 to k, j going from 1 to m, is this a measurable partition? So there are two things. First I have to show that all the Cij's are disjoint, and that Cij's are mutually exclusive and exhaustive. That is one part. I have to show it's a partition. And second part is, we have to show it is measurable. Means we have to show that every Cij is in script A. Now second part is easy because we know every ai is in script A, every bj is in script A. So because script A is a sigma field, intersection of any two sets from it would also be in script A. Okay, so measurability is easy. Now to prove that it's a partition. So how do we prove it's a partition? We need to check first whether they are exclusive. So if I have Cij intersected with Ci prime j prime, then this would be written as ai intersection bj intersection with ai prime intersection bj prime. We know ai is a partition, so this is disjoint and this is also disjoint. Hence, the overall intersection is empty. Okay. Even if I keep one subscript common, so if I make it Cij prime, it would be ai intersection bj intersection ai intersection bj prime, which actually becomes ai intersection bj intersection bj prime. Now even if ai is there, still bj prime becomes phi, so it becomes ai intersected with phi, so it is finally phi. Okay. So even if you change just one subscript, still they are disjoint. And now we have to prove that their union is entire omega. So union over Cij, I going from 1 to k, j going from 1 to m. So this becomes, sorry, this is union. Okay, union over j going from 1 to m, union over I going from 1 to k, ai intersection bj. This could be written as union over j going from 1 to m, union ai, I going from 1 to k, whole intersection with bj because j is free from I. Now since ai is a partition, union of ai is omega. So this becomes omega intersection bj, and omega intersection bj is just bj. So I am left with union over j going from 1 to m bj, which I know is omega because bj's also form a partition. Okay. So what we have proved just now is Cij forms a partition. If you are not comfortable with the notation Cij, you can call it say mk, and then k goes from, sorry, not mk, some mr, where r goes from 1 to product of km. Okay. So we have proved that Cij, I and j in appropriate limit forms a partition. And now the new random variables, that is x1 plus x2, x1 minus x2, x1 into x2 and x1 by x2, they are measurable with respect to this new partition. Okay. So x1 plus or minus x2 can be written as sum over j going from 1 to m, sum over I going from 1 to k, ai plus or minus bj, indicator of Cij. So on Cij the value will be ai plus bj. We saw that in the picture. Okay. So how many distinct values does x1 plus x2 have? The number of distinct values is at most k into n. Why I am saying at most? Because some of the values might be same. Because ai plus bj might be equal, for example, a1 plus b2 might be equal to say a4 plus b1. Something like that might happen. In that case, we may have same value on two Cij's, but that is fine. Okay. So we have x1 plus or minus x2 as this. Okay. Same story will go with x1 into x2 and x1 by x2. So x1 x2 would be sum over j, sum over I, ai, bj, indicator of Cij. Okay. Same with x1 by x2. So what we have proved is addition of two simple random variables is a simple random variable. Subtraction of two simple random variables is a simple random variable. Similarly, product and division. Okay. Now there are two more important results. So let x be a random variable defined from omega script a to r script b. Okay. X be a random variable. Now I am not saying x is simple. X is any random variable defined from omega script a to r script b. Okay. Now the result says that then there exists a sequence of simple random variables. There exists a sequence of simple random variables xn on omega script a, defined on omega script a, such that xn converges to x. Okay. Now there are there is one thing that we don't know. What do I mean by xn converges to x? Okay, we have not actually defined the convergence. Okay, so let me go to that. Convergence, but I will focus on what is known as point-wise convergence. There are many ways in which a random variable sequence can be convergent. We are going to study those ways later, but today we need just point-wise convergence. So what do I mean by point-wise convergence? Let us again go to the definition of random variable. So you define a random variable from omega script a to r script b. So any random variable first is a function from omega to r, right? And now we want a sequence of random variables. So what I am going to have is x1. For the sake of convenience, let me say omega has omega 1, omega 2 up to omega k. Okay, let us assume, for the sake of convenience, let us assume that capital Omega consists of only k elements. So when I consider sequence of random variables, I will have x1 omega 1, x1 omega 2, and in this direction I can write x2 omega 1, x3 omega 1, similarly xn omega 1 dot dot dot. Then I'll have x2 omega 2, x3 omega 2, xn omega 2 dot dot dot. Then x1 omega 3, similarly x1 omega k, x2 omega 3, x2 omega k. So what do I mean by this? See, when I consider sequence of random variables, for every omega 1, I am actually getting one sequence of real numbers. x1 omega 1 is some real number, x2 omega 1 is some other real number. Okay, so if you fix omega, so for omega 1, let's say, this is a sequence of real number. Similarly, for omega 2, the second row is a sequence of real numbers. If I fix omega 3, the third row becomes sequence of real numbers. Right? Because if you fix omega, then you have x1 of that as some value, x2 of that as some other value, x3 of that as some other value. So this entire row becomes a sequence of real numbers. Similarly, this row is another sequence of real numbers. Okay? Therefore, sequence of random variables is actually a collection of many sequences of real numbers. How many? The number of sequences would be same as number of elements in omega. So here I have k small omegas, so I am getting k real sequences. If I had infinitely many small omegas, I would get infinitely many sequences. Are you with me so far? This is slightly different type of discussion, but you must have come across it in real analysis. In real analysis, when you talk about sequences of functions, this is exactly what you do. Okay, x here is a function. In fact, that's why we have the sequence and uniform convergence, etc. Okay, so when I talk about sequence of random variables, we have to talk about collection of sequences of real numbers. Now what happens because of this? When I want to talk about convergence, this first real sequence might converge to something. Okay, let us assume for the sake of convenience that each of these real sequences converges. So this real sequence might converge to some x of omega 1, some value which we will call as x of omega 1. This second real sequence will converge to something else. We will call that value as x of omega 2, this as x of omega 3, and so on. x of omega k. Is it okay? And this final thing, so basically if I collect all these limiting values, I don't have a single real number. For every omega I have one real number. So this kind of becomes a function x of omega, which is defined from omega to script r. Okay. Let me try to take one example to make things a bit more clear. Okay. So let omega be outcome of a die throw. So I have 1 to up to 6. And let me define x and omega as omega plus 1 by n. Okay. Let me define x and omega as omega plus 1 by n. So x and omega has to be a function of both omega and n. Now, how would I get the sequences? So, when I fix omega at omega 1, so if I consider the sequence x and omega 1, I have 1 plus 1 by n as a sequence. 1 plus 1 by n means I have 1 plus 1 by 1, then 1 plus half, 1 plus 1 by 3, 1 plus 1 by 4, and so on. When I fix x and omega 2, it becomes 2 plus 1 by n. So 2 plus 1 by n is equivalent to 2 plus 1 by 1, 2 plus 1 by 2, 2 plus 1 by 3, and so on. Similarly, I have 3 plus 1 by 1, then 4 plus 1 by 1, etc. This sequence converges to 1, this converges to 2, this converges to 3, this converges to 4. Okay. So if I try to combine all this, what I get is limit over n going to infinity, xn of omega is actually x of omega, where x of omega is 1 if omega is 1, if x of omega is 2 if omega is 2, x of omega is 3. So basically here x of omega is omega, and you can see it makes sense. If I take limit as n going to infinity here, I do get omega. Okay. So we are talking about convergence of every sequence of real numbers that is part of this collection. Okay. Hence this is known as point-wise convergence. Okay. So this is known as point-wise convergence. Why? Because for every fixed omega, you can say x and omega goes to that particular x omega. Okay. So even if you change one x omega, it won't work. So if you define, say, in this die example, if you define x of omega is equal to, say, 4 when omega is equal to 3, and everything else you keep same, means for every other omega, if you define x of omega as omega, still, because in this thing it won't work, because for this particular omega it is not working, we will have to say that the sequence doesn't converge. And as I said, we are talking about convergence of every row. Okay, so for every omega I have a real sequence. So we can extend that definition. What is the definition of convergence of a real sequence? Convergence of a real sequence tells me that, let me write down that definition. So given epsilon greater than 0, there exists n naught in n such that mod of xn minus x is less than epsilon for every n greater than or equal to n naught. This is definition of convergence of real sequence xn. Okay, if you are getting confused with the notation, you can make it an minus a. Okay, so that they are real numbers. Now here, for every omega I have one real sequence. So I have to talk about convergence of all of them together. Okay, so what would I do? I would say, given epsilon greater than 0, there exists n naught which depends on omega, and of course it depends on epsilon, because here also n naught depends on epsilon. such that mod of xn omega minus x omega is less than epsilon for every n greater than or equal to n naught and for every omega in omega. Okay, so the convergence should happen for all omegas. So you have to kind of take, so if we are in the earlier die example, for every omega you might get one n naught because for every omega you have one real sequence, and you then kind of take maximum of n naughts so that beyond that n naught everything is possible. Means every xn minus x omega is less than epsilon. Okay, such a maximum, here it is finitely many, so I could take maximum. When you have a countable or uncountable collection, it would become supremum. So it may or may not exist. So even if every sequence converges, you may not have overall pointwise convergence. Okay. So if you can think of a common n naught which works for all omega, this would be known as uniform convergence. Okay. Why uniform convergence? Because you have a common n naught which works. Right now I have said it is dependent on omega. But if you can take such maximum, which means you can take a common n naught which works for all omegas, then you will say it's a uniform convergence. Okay. So if your omega is changing n naught, then it's usual pointwise convergence. However, if you can take say supremum over all omegas or maximum over all omegas and get one n naught which works for every omega, then you can call it as uniform convergence. Okay. So this is some idea about pointwise convergence of a sequence of random variables. The important takeaway from here is that a sequence of random variables is a collection of sequences of real numbers. Okay, it's not like a single real sequence. Okay. Okay, so let me go back to the result that we were stating. So we stated that if x is any random variable, then there exists a sequence of simple random variables converging to x. Okay. And in fact, there is one more similar result. If x is a non-negative random variable, then there exists a non-decreasing means actually increasing sequence of simple random variables, non-negative simple random variables, such that random variables xn, such that xn converges to x. Again, this is pointwise convergence. So for every omega, xn omega converges to corresponding x omega. So if x is non-negative, we have additional information about this xn. Every xn is non-negative and it's a non-decreasing sequence. Non-decreasing sequence means x1 for fixed omega is less than or equal to x2 for that omega is less than or equal to x3 for that omega, and so on. Okay. So these two are important results, that given any random variable, we can construct a sequence of simple random variables converging to it. As a consequence of this, we can extend some properties of simple random variables to all the random variables. Okay. For example, we proved that if x1 and x2 are simple random variables, then x1 plus x2 is simple, x1 minus x2 is simple, etc. So now we will extend that to any random variables. Okay. So let x1, x2 be any two random variables defined on omega. Okay, x1, x2 be any two random variables defined on omega. Then x1 plus minus x2, x1 into x2 and x1 by x2, provided it is defined, means you don't have 0 in the denominator ratio, are also random variables with respect to same omega script A. Okay. Is it okay? So how do we prove this? We are going to use the results that we stated just now. So x1 is a random variable means there exists a sequence x1n of simple random variables such that x1n converges to x1. Similarly for x2, there exists a sequence x2n of simple random variables such that x2n converges to x2. And now we have x1n plus x2n will go to x1 plus x2. Why? Because they are collection of sequences of real numbers. Okay. So we know for every fixed omega, x1n omega plus x2n omega, I am fixing, so I am writing omega naught, will go to x1 omega naught plus x2 omega naught, and this is true for every omega naught. So overall I can write this. Okay. And what makes this a random variable? Because now you have this as a sequence of simple random variables again. See, x1 is a sequence of simple random variables, x2 is a sequence of simple random variables. Sorry, x1n is a sequence of simple random variable, x2n is a sequence of simple random variable, and we have already proved that addition of any two simple random variables is a simple random variable. So, x1n plus x2n is a sequence of simple random variables, and x1 plus x2 becomes limit of that sequence, and we know that limit of a sequence of random variables is also a random variable. We discussed at the beginning of the lecture, this lecture itself. Limit of a sequence of random variables is also a random variable. Okay. So x1 plus x2 is limit of x1n plus x2n. This is a sequence of simple random variables, and hence its limit is also a random variable. Okay. Same story you can write for x1n minus x2n, x1n into x2n, and x1n by x2n. Is it okay? Now we have one more similar point. We are going to define positive and negative part of random variables. Okay, what do I mean by positive and negative parts of random variables? So x plus positive part is defined as maximum of x comma 0. X minus is defined as maximum of minus x comma 0. Okay, these definitions might be slightly tricky to understand. Let me explicitly write, it is an easier way. So basically what I am doing, I am defining x plus omega as x of omega if x of omega is positive, and it is defined as 0 if x of omega is less than or equal to 0. Okay. So we are taking value x only if it is positive, otherwise we are setting it at 0. And in case of x minus omega, we define it as minus of x omega if x of omega is negative, and 0 if x of omega is positive. So what we are doing is we are taking the negative part, okay, negative part, but we are making it positive by multiplying it by minus sign. X of omega is negative, so minus x is positive. Is it okay? Let me take one example. Suppose x of omega is defined as 1 if omega is equal to head, and it is defined as minus 1 if omega is equal to tail. Okay, suppose we are talking of coin toss. So x of omega is defined as plus 1 if omega is head, and it is defined as minus 1 if omega is tail. Then what are the positive and negative parts? So x plus omega would be 1 if omega is equal to head, because it's a positive part, so I retain it as it is, and it is 0 if omega is equal to tail, because it's negative, so in contribution of negative part becomes 0. Okay. Similarly, x minus omega would be 0 if omega is head, because I don't want any positive things coming in here, and it becomes minus of x omega. So minus of this minus 1, so it becomes plus 1 if omega is equal to tail. Okay? Is it okay? The interesting thing is, you can try to verify this on your own. So I can phrase it as homework. So homework is, x of omega is actually x plus of omega minus x minus of omega. Try to first verify in this example and then try to write the general proof. And mod of x omega is actually x plus of omega plus x of omega, x minus of omega. Okay, try to prove these two things. It's a good homework. Okay, and now we are going to claim that x plus and x minus are also random variables. Okay, so how do we do that? How do we write down the proof? Now from definition, there are two ways in which we can write the proof. So from definition, we can say that it is maximum of two random variables. X plus is maximum of x0, x minus is maximum of minus x0, and we have already proved that maximum of any two random variables is a random variable. So x is a random variable and 0 is a degenerate random variable. Similarly, minus x is a random variable and 0 is a degenerate. So maximum of any two random variables is a random variable. Okay. There is another way. You can try to write this down as indicator function. Okay. So another homework. Try to see if x plus can be written as x into indicator of x greater than or equal to 0, and check whether this is correct, and try to get similar representation for x minus. Okay. So today I will stop here. Thank you.